Let us talk about this problem. We are given a binary tree. We need to check if the given binary tree is height balanced or not. What do we mean by height balanced? Height balanced means the difference between heights of left subtree and right subtree should not be more than 1. And this should be true for every node. Let's see this tree for example. If you see this node, the height of left subtree is 1, the height of right subtree is 2, and the difference is 1. So this is fine for this node. For this node, there are left and right subtrees both empty, so it's 0 for this. If you see this, the difference for this node is 1 minus 1, 0. Let's see this. The difference between left and right heights, left subtree has height 2, right subtree has height 0. So the difference is 2, which is more than 1. So that is why the answer is no. Let's see this. Difference between left subtree and right subtree heights. Left subtree height is 2, right subtree height is 3. So this is fine. Let's check this node. It's 0, the difference between left subtree and right subtree for this. So this is also fine. Let's check this node. For this node, the difference between left subtree height and right subtree height is 2, because left subtree height is 0 and right subtree height is 2. So we say no. If we find any node for which difference between left and right subtree heights is not smaller than or equal to 1, we say it's not height balanced. Let's see this tree. For this node, the difference is 1. The left subtree had height 3 and right subtree has height 2. For this node, the difference is 1. Left subtree has height 1, right has height 2. For this node, the difference is 1. For this node, the difference is 0. For this node, the difference is 0. For leaves, it's anyways 0. So our output is yes. This is a height balanced tree. Now please pause this video and try to write down a solution for this. We are going to talk about two solutions for this problem. One solution is going to be big O of n square and other solution is going to be big O of n. Let us talk about the naive solution first. So the idea of naive solution is simple. We begin with the root. We compute the height of left subtree, compute the height of right subtree. We check if the difference is less than or equal to 1. If that is true, then we call is balanced recursively for the left subtree to check if the left subtree is also balanced, and we call is balanced recursively for the right subtree. So if all these three conditions are true, then we return true. Which three conditions? First thing is the difference between heights of left subtree and right subtree should be less than or equal to 1. Left subtree should be recursively balanced. The right subtree should be recursively balanced. That's the basic idea. Now what is the time complexity of the solution? You are going to call height function for left subtree and height function for the right subtree. Height function for a tree with n nodes takes big O of n time. So you are just leaving one node and then you are calling height function for remaining n minus 1 nodes, which is going to take big O of n minus 1 time. So overall time complexity of this solution is going to be big O of n square, because is balanced is going to traverse every node, and for every node we are going to call height function for left and right children both. So that is how the time complexity is big O of n square. We have just talked about a big O of n square solution. Now please pause this video and try to think of a solution that works in big O of n time. The idea of big O of n solution is, what if your left child call and right child call, these two calls not only tell you whether they are balanced or not, they also tell their heights. They do two things. So every recursive call or every function call in fact does two things. It tells if that particular subtree is balanced or not, and it also returns the height. We can implement this efficient solution by simply returning a pair where first value of this pair is a Boolean value which tells you whether the subtree is balanced or not, and the other value is height. An interesting and tricky implementation is to return only one value, one integer value, and we say this function is going to return -1 if this tree or subtree is unbalanced. Otherwise, it's going to return height. So height is always 0 or positive. So by one value, we can do both the purposes. Now please pause this video and write a function that returns an integer value. This value is -1 if this tree is not balanced, and this value is 0 or positive if this tree is balanced, and this positive value indicates height of this tree. Here are big O of n implementations of this approach. We have two implementations, one in C++ and one in Java. The most important thing here is to note the return type is integer, and these functions, they return -1 if the tree is unbalanced, otherwise they return the height. Let's now talk about the logic used in these implementations. We begin with the root. To check if the root itself is balanced or not, we need to know the height of left subtree and we need to know the height of right subtree. To know the height of left subtree, we recursively call is balanced for left subtree. And this recursive call will return height if the left subtree is balanced, otherwise it will return -1. So if this call returns -1, then we immediately return -1, that this whole tree cannot be balanced because there is a node which is unbalanced, right? So if it returns a positive or 0 value, then we are fine. Then we call for the right subtree to get the height and check if the right subtree is balanced or not. If right subtree returns -1, then we immediately return -1 because this whole tree cannot be balanced. If you see this tree, for example, the right subtree is going to return -1 and the output for this tree is not balanced because the right subtree has this node for which the difference between left and right heights is more than 1. Left height is 0 and right height is 2. So we call for the left subtree, check if it is balanced or not. If it is balanced, then we use the left height, returned value. We call is balanced for the right subtree. If it returns -1, then we immediately return -1. Otherwise, we use the right height. Using the left and right heights, we check if the node is balanced or not. So before checking for the current node, we check for the left subtree hole and we check for the right subtree hole. And if these left subtree and right subtree, any of these are not balanced, we return -1. And if both are balanced, then we check the current node. So if you see these codes, these lines, here we are checking whether the left subtree is balanced or not. If we are getting -1, we are immediately return -1 for the whole function. Otherwise, we are going to use this left height to check for the current node. Then we do the same thing for the right subtree. And at the end, we check the current node, if the current node is balanced or not. If the current node is not balanced, then we return -1 to indicate that this subtree is not balanced or this tree is not balanced. Otherwise, we return the height of current node because current node may be root of a subtree and its parent would need height. Let's do a dry run for this tree. We begin with 8. So we call for the left subtree first, right? We begin with the first line, this is not null. So we come here and we call for the left subtree. Left subtree is also not null, not going into the base case. So it will call for 13. Now when you call for 13, 13 is going to again not null, so not going into the base case. It's going to call for the left subtree which is null, and null is going to go into the base case and going to return the 0 as height. Then 13 is going to get the control back and it's going to call for the right subtree, and right subtree is also null, so right call also returns 0. So we are here in the execution. We have the left height as 0, right height as 0. We are not in these cases where they are negative because we have got non-negative value. Now we check for the current node. Is this balanced? Yes, it is balanced because the difference between left height and right height is 0. So we return height of this subtree, and height of this subtree is maximum of 0 and 0 plus 1. So this returns 1 as height to the parent call. Now this call gets the control. It has done the left call, and the left call has returned a positive value. So it does not go into the if case where we are returning -1. Now it's going to call for the right subtree of it. When it calls for the right subtree is also a leaf. So it's going to get 0 from here, 0 from here. It's going to return 1 to its parent, right? Now this call has got a non-negative value from right call also. So left and right are fine for this tree. Now it's going to check itself. Am I fine? So the difference between 1 and 1 is 0. So it's fine itself. It's going to return the height, which is maximum of 1 and 1 plus 1, 2. So it returns 2 to the parent. Now parent has called for the left subtree. The control comes to the parent here. it has called for the left subtree. Now it's going to call for the right subtree. When it calls for the right subtree, it's going to call for this 15. And when it calls for the 15, it's going to call for the left child of 15, which is null. So it's going to return 0 to the parent, right? So the left call is going to return 0. Now it's going to call for the right subtree, and right subtree is 16. Right subtree is going to call for the left of it, which is null, so it's going to return 0. Now this is going to call for the right of it, which is the leaf, so it's going to return 1. Its left will return 0, right will return 0. It will take the maximum of these two and will return 1. Now 16 is going to take the maximum of 0 and 1, which is 1. It's going to add 1 to it and it's going to return 2. So this gets the left height as 0, right height as 2. So this is going to return -1 because the difference between left height and right height is greater than 1. So it's going to return -1 to its parent. Now the parent has a value -1 from the right call, so it is going to fall into this if condition that right height is returned -1. So it's not going to check for itself, it's not going to execute this line, it's immediately going to return -1 to the caller, that I am not a balanced tree. So this is how this code works. What is the time complexity of the solution? We are traversing every node exactly once, and when we traverse a node, we do constant amount of work. That is how the time complexity of the solution is big O of n.